Welcome, ladies and gentlemen, to FaceHaptics, robot arm-based versatile facial haptics for immersive environments by Alexander Wilberz, Dominik Leschtschow, Christina Trepkowski, Maiero, Ernst Kruijff and Bernhard Riecke. In this paper, we explore haptic feedback towards the human face to improve presence and emotional response. With our system, we aim for a flexible solution to enable provision of highly versatile cues and to support the user to walk around in a relatively unencumbered way. The specific focus of our system is on localized and fully directional cue provision at the face instead of just around the eyes itself by adding a robot arm to the HMD that can provide stimuli below the HMD itself. As such, we can provide different types of actuation from different directions towards the face. So let's take a look at related work. In our system, we deliberately look at the provision of haptic cues. Previous systems mainly have attached or integrated actuators inside the HMD or below the HMD to provide wind, thermal cues, vibration, or even suction, inertia, and pressure. Only very limited research has been performed on chemical senses by attaching olfactory displays to a HMD to provide smell, or even to allow people to bite objects, food, to enable food experiences. There's also some related work in other mechatronic solutions that relate to our robot arm, especially those that have been attached to mobile devices to the body itself, or even the usage of drones that can provide haptic cues towards the user's hands. Most of these systems have certain limitations that we try to overcome with our system, specifically the range and location of actuation, the effect of actuation, the variety of cues, especially provided by a single system instead of providing various cues in a system over time. So let's take a look at the system itself. The robot arm is a 4 degree of freedom robot arm using linear actuators and servos and can be calibrated for face geometry. Actuation consists of a touch actuator, maximum 5 Newton, wind, heat element, and a spray nozzle that can spray water towards the face. The system is operated at 45 degrees per second to limit vibration at the HMD itself, and the overall weight is 405 grams. However, we do have a counterweight behind the head to balance out the HMD with the system in the front. We performed 2 user studies to assess our system. In the first study, we looked at directional wind cue perception, looking at how well users can perceive directional haptic stimuli towards the face, and in part looking at how dynamic head movements can improve accuracy of perception. In the second study, we looked at user experience to basically look at how adding different face haptic stimuli affect user experience in comparison to audiovisual stimuli only. In study 1, we investigated how well participants could judge the direction of wind. To do so, we assessed the effect of head movement and if the FaceHaptics robot arm would compensate for head rotations or not. We had 4 different conditions, which you can see in the graphic on the right side. The first condition, static head, where wind rotated around the head in a static position. Then we had 2 oscillating head conditions, where the head oscillated by following a butterfly target, either with compensated wind or with static wind. And then we had a free head movement condition, where the user could move their head at free will and had the wind compensated again. Directions were grouped in the 3 areas in front of the face, and judgment was done after the cue had finished after 8 seconds, where the head had to be pointed towards the direction of wind. In total, there were 24 trials, 3 wind directions, 4 conditions, and 2 repetitions. Now let's take a look at the results of study 1. The absolute pointing error was lowest for free head movement and highest for conditions with static wind direction. We found no main effect of wind direction and also no interactions between movement condition and wind direction. The variability in pointing data was similar to absolute pointing errors, and the certainty of judging was highest for free head movement, but no effect of wind direction or uncertainty was found. The bottom line is that we found a good directional judgment comparable to, but slightly higher than Nakano et al. That had a slightly different setup, also with a different wind flow shape that affected wind direction perception. In study 2, we compared the effect of audiovisual cues and multisensory cues on user experience. Users were moved over a scripted path with 16 clearly noticeable events, each associated with a specific type of cue. During the experiment, users wore noise cancellation headphones to filter out ambient noise. Each path durated approximately 3 minutes. After the experiment, users answered questions from a questionnaire about convincingness and memorability of events, emotional response, awareness of events, effect on visual experience, associability of events, and presence. Now let's take a look at the results of study 2. Presence, memorability, believability, and enjoyment ratings were all significantly higher with multisensory cues in comparison to audiovisual cues, with some variations between events. We also found that valence and arousal was higher for multisensory, and we also found another type of emotional response, namely disgust. What was also very interesting was that haptic cues had a positive effect on the experienced visual realism of the environment in comparison to the audiovisual condition only. The bottom line here is that improvements are somewhat as expected, however, the effect seems to be bigger on emotional response than on presence, and the effect on visual realism is interesting but needs to be assessed further. What's also important to note is that directionality was rated as important, but also that cues can be further improved. Overall, however, we showed the importance and usefulness of our cues in this study. Now let's take a look at the technical considerations and limitations of our system. We briefly go over some of the major findings of our system in comparison to other systems that are connected to the body, as can be seen on the left image, to the surface, like a robot arm mounted on a table, or systems that are mounted on a drone. If we take a look at different types of factors like weight, operation speed, accuracy, safety, but also ergonomics, we see that there are differences between the different systems, where our system is quite flexible, however has limitations, for example in weight and operation, however can provide different cues in a far more wider range than other systems that, for example, are mounted on a table. For more details, please refer to the paper. Now let's take a look at the outlook of the paper. There are certain limitations that can be overcome by hardware iterations. First of all, we would like to take a look at reloading mechanisms that can reload a specific type of stimuli. There are some examples in real work that can be used for this, for example the rotating head of the haptic revolver by Maiero, or magnetic exchangeable heads similar to the Bobo. We would also take a look at different types of actuations or events, for example to add olfaction, to play around with different soft and hard actuations, and also to focus on other types of events, for example fear-inducing events or pain that can be used in therapy or game environments. Finally, we would like to redesign our system to relocate some of the hardware towards the top of the head to alleviate some of the weight issues that we can find in our current design. In conclusion, we presented a novel haptic actuation system for versatile cues towards the human face. We showed how well people can judge directional cues and how the system affects immersion and user experience. Thanks for watching, and for further details please refer to our publication.